Now let's set up our experiment to investigate Faraday's law a little bit more quantitatively. We're going to be looking at the EMF produced across the coil, this coil wire, the solenoid. Here's the leads, the two ends of the wire that are wrapped around this tube back and forth. So we want to apply a magnetic field inside the loop of wire and measure the voltage across the ends of the wires. So measuring the voltage here, what's going to produce the magnetic field to apply through the center of the solenoid is a larger solenoid. So we're going to run a current through the wire here. See, it's thicker wire, so we can apply a large current, a larger gauge. So run a current through here, and that will create a magnetic field inside the large solenoid. And then if we put the small solenoid inside the large solenoid, there will also be a magnetic field through the small one, and we can measure the EMF, the electromotive force, across the ends of that wire and make up the small solenoid. Okay, so, and remember we want our current and therefore the magnetic field to be time varying, as we saw in the first video. A time varying magnetic field is necessary to create an EMF in the other solenoid. So first let's set up how we're going to create a time varying current in the larger solenoid in order to create a time varying magnetic field. So we're going to use the function generator, which outputs a time varying voltage. So here I have a BNC to alligator clip cable. So the BNC side will go on the output of the function generator. And then if I take the alligator clips and attach them to the ends of the solenoid, then we have a complete circuit there. One thing I want to add here, we want to measure the current going through the large solenoid, and we have the oscilloscope, which measures time varying voltages, but we want to measure a time varying current. So one way we can do that is to take advantage of Ohm's law and use a small resistor, a resistor with a small resistance, and put it in series between the solenoid and the function generator. So I'm just going to stick it on one of the leads here. And then if we read the voltage across the resistor, we can use Ohm's law, V equals IR, to translate the voltage into a current. Now the value of this resistor, the resistance, is 1 ohm. So then V equals 1 times I, so V equals I. So that's a convenient choice of resistance for us to use. We basically can now look at the voltage across this resistor, and that will be the same as the current running through the large solenoid. So let me get this cable out of the way. The way we're going to measure that voltage and equivalently the current is with the oscilloscope. So here I have an oscilloscope probe with also a BNC cable on one end and the probe on the other, and it has a little hook that you can hook onto a lead, and it also has a small alligator clip for the ground. Now this is going to be attached to the ground. That's something I screwed up last time, so it needs to go on the same part of the circuit as the ground from the function generator, because they're both tied to the building ground, sort of the long third prong on a normal electrical plug. So I'll plug the oscilloscope probe here onto channel 1 of the oscilloscope, and that will be yellow on this oscilloscope. It'll come up as a yellow waveform. And I'll put the alligator clip on the ground side of the resistor, and the probe clip goes on the higher voltage side of the resistor. Okay, now if I turn on the function generator, we should be able to see the waveform pop up on the oscilloscope. You can also see the circuit diagram is written here. So far we've done the left-hand side. Function generator, outer solenoid, resistor, and across the resistor to the oscilloscope. Then the other thing we're interested in is the EMF. The thing we're really measuring is the EMF generated across this solenoid, the smaller solenoid, as we put it in the magnetic field generated by the larger one. And to do that, we have a third type of cable, also BNC on one side. Then it goes to these banana plugs. So, and they fit perfectly here in this smaller solenoid. And that will go on channel 2, so we can see. Oh, no, I can't see channel 1. So then we can see the EMF in generated on the smaller solenoid in blue here on the oscilloscope screen. So let's turn on the oscilloscope. It's on, but I can turn on channel 1. And you see that okay? So this is channel 1. This is the current running through the larger solenoid. I have the function generator set to around 500 hertz sine wave, like a medium output level. And we can look on the screen and it's saying the frequency gives a much more accurate, or precise at least, display of the frequency, 526.8 hertz. Some fluctuation in the last digits there. Let's measure the current. So here, not sure you can see that small writing. It's the scale, the vertical scale for channel 1, and it says 50 millivolts. So each one of these 1 centimeter squares is 50 millivolts. So we have about 50, 100, say 125 up, and 50, 100 down. So that's 100 and 125, 225 millivolts peak to peak. And because of the 1 ohm resistor, that's the same thing as 225 milliamps. So we have 225 milliamps. That's the peak to peak value running through this large oscilloscope. And we can measure that using the cursors too to get a more precise measurement. So I'll move the top cursor up to the top peak and then select the bottom cursor and move it down to the troughs. And this delta value tells me 228, it says millivolts, so 228 milliamps. As far as this resistor actually has a resistance of 1 ohm, which we can measure later. Okay, now let's turn on channel 2, which is just right now a flat line because there's no EMF here. But as I bring it closer, subject it to a magnetic field, time varying magnetic field, you can see there is an EMF induced. So our first variable that we're going to look at will be varying the magnetic field through the smaller solenoid by changing the distance between the two solenoids, with zero distance being fully overlapped.